Well, the free text helps if there is a very negative score. We take a close look at the free text. If the score isn't negative, then we typically don't read every detail. But in my experience, like when I was teaching larger classes in this was kind of a very valuable tool just to see who was doing something. Because, like, unfortunately, there's always teams that don't work well, and where one person thinks he can essentially coast through the assignments.
I guess that's an incentive to keep the teams kind of small so that everyone has to do something.
Yeah, and also like smaller teams, I think teamwork is valuable, but bigger teams kind of like create a lot of overhead.
we're good.
Okay, we're good to go, great. So today we'll spend probably half of the lecture finishing up the graphs, and then I will talk about maps. Are there any questions from like an organizational perspective, projects, assignments, other than what we just discussed? If not, let's just keep going. We talked about graphs last time, so I'll just recap the most important things that we covered last time. As with any kind of visualization, when we talk about graph visualization, it's essential to think about the interaction of the data and the task, because this is actually what makes you choose your graphical representation. So you have graph data, and then you have certain goals and tasks, and what the tasks are and what the data are influences your choice of graphical representation. And then we talked about a couple of different kinds of tasks, and the thing that I would like you to remember here is the distinction between attribute-based tasks and topology-based tasks. These are really important. So topology-based tasks are anything like neighborhood finding, identifying clusters, identifying articulation points, identifying connected components, identifying disconnected components, and so on. And attribute-based tasks deal with node and edge attributes. So it's very common in real life graphs that you have a rich set of attributes for every single node or even for every single edge. Let's just say we talk about the social network. The attributes would be the names of the people, their age, then anything like which clubs do they belong to, where did they go to school, and so on. But could also be completely numerical attributes. Like in biology, you very often have experiments that, like for example, that measure gene expression, and you can map those values to individual nodes in a protein interaction network. So I'll have an example for that later. So really this distinction is very important because it goes back to like what is your goal, what is your task, what is your data, and therefore what is your graphical representation. So I introduced that we have three different kind of graph representations, and we kind of talked a bit about the explicit and node link diagrams last time. Then we will talk today about matrix representation and about implicit representations, whereas implicit representations don't really work for general graphs, they only work for trees with some, basically they only work for trees. So explicit graph representations are node link diagrams, and here we have three different classes with the free layouts where we can essentially position the nodes however we like. That essentially gives us the best possible layout. We have the style layouts where we, for example, align the nodes along a grid or along a circle and then draw the edges along them. And then we have the fixed layouts where we can choose our node positions, and that's usually important if you have some spatial context, as you can see here. Then we talked about various criteria for good node link layouts. So for example, minimize edge crossing, minimize the drawing area, uniform edge length, and so on. And we talked that these criteria are conflicting. So you can't find a global optimal solution for all of these. So here we have examples for like space utilization versus symmetry. So like here we make use of as much space as possible, but here we have like this one here is symmetric to substructure here, is symmetric to this substructure here. Okay, I talked enough about force-directed layouts. They're kind of important, but they're usually not the best layouts. And then we talked about the giant hairball problem, where we have a lot of nodes, and that simply makes it impossible to make a sensible graph visualization. So the approaches to tackle this here would be things like aggregation or filtering, query-based approaches, similar to whatever we talked about large data sets. We need to be smarter about what we show to be able to actually show something at all. Let's skip over this. And here we had like this idea of collapsing nodes into supernodes. So you could dynamically like pick any point here and simply like aggregate all of the points, all of the children into a super node. This is an example for like an improved layout, an orthogonal layout, which I showed you. So then we talked about restricted layouts in the circular layout example. You can see that this is pretty sensitive, as any graph visualization technique, to the connectedness of the graph. Like a completely connected graph is essentially just a black sphere here, or black circle. And here, like, this is what it looks like with 3% of edges, and here 6% of edges. I'll skip over this. And then we talked about edge bundling. And so the idea of edge bundling is, in this case, it uses a hierarchical structure to route the links between, like based on the hierarchical structure that you can see here in the background. So these are the individual, this is a software repository, these are individual files, these are packages, and these are higher level packages. And so like there's a tree, essentially, like you can think of a tree that is built in here, like a radial tree, and these links are routed along along the backbone of the tree. So if you, for example, want to connect something from here to here, you wouldn't go straight, you would go like up here, then there, then there, then there, then there, then there. So that's kind of the fundamental idea of the hierarchical edge bundling. And then you can have various bundling strength factors that you can essentially modify how close your spline fits to this tree outline. And these are like a couple of examples of varying bundling strengths variables. So you can see like here it's completely relaxed and here it's very tight. And typically a compromise solution is the best here. So for fixed layouts, fixed layouts are a little tough because you can't really vary the position. So all you can do is mainly like draw links between the various elements. But then you can also think of bundling. So this here is not a hierarchical edge bundling, but this is a force-directed edge bundling. In this case, the edges, like each, like how that works is that each segment of the edge, like or each edge, is divided into multiple segments of equal length, and these segments attract each other, similar to like the force-directed layout of a regular node link layout. And then you get results like this. And as I mentioned, it's not quite clear. Like the benefits of these layouts is not very obvious. I think it's cleaner in this case, but I guess in the general case it's a little tough to judge. Okay. Okay, I think this is where we stopped. So now let's talk about multivariate graphs, and this is really about edge attributes. So, or node and edge attributes. So like the basic thing you could do with node attributes would be, of course, coloring. So let's say you have categorical data, as you have here, like this is, again, the Les Miserables graph. So you have the various like groups of people colored in blue or pink or green or yellow and so on. So that makes a lot of sense. So if you have like a sensible clustering, this is essentially a clustering, if you have a sensible grouping, then coloring is a very good choice. Of course, if you have more data than only like single categorical assignment, if you have like numerical data, and if you have like a large vector, things get a little bit more tricky. So people try to do glyphs. So here's an example where somebody tried to do pie charts, well, this is actually not a pie chart because it just like shows you the size, like these are 4 different variables, and by how big the segment is filled out, that is kind of like the idea here to show you this variable. So this here, all 4 variables would be high, here all 4 variables would be low, and so on. So this works. It works for 4 segments, maybe for 5 or 6, but it's not like very efficient, of course. You can see that they're like, what are the values of this circle here or this circle here? So you need to like compromise your layout, essentially. There's other approaches to do that. So here are little spheres packed into like nodes. You can see this is a very thin sphere. These are thicker spheres. And here we have like various colored circles. Here is a mixture of these circles and little bar charts below them. Here are little bar charts within the nodes. Here are little line charts within the nodes. and here little bar charts with error bars within the node. So all of these are from the biology domain. So you can see that this is like a very common problem in biology for reasons that I'll talk about soon. We talked about small multiples a while ago, and I've shown you this picture, but I'll show it to you again now. So small multiples really help you to really like map a couple of variables and see the differences. So here you're really good, like here you have an overview, and then you have two multiples that map different, essentially, examples. So you can see, for example, this node here is red in this condition, it's blue in this condition, and it's blue in this condition. So you can do these comparisons. And of course, small multiples have the advantage that you see every single view as it's supposed to be. But comparing between them is really very manual. So if you, let's say, if you don't really get a good idea of what is the overall trend. So if you want to compare, okay, this cluster here, okay, it looks pretty red, but then here, oh yeah, there's like one list of blue elements. So you have to do this very conscious effort of comparing things here. And of course, their scalability is limited. So if you have 3 or 4 or 5 data points that you want to map, and if it's really important for you to also be able to see the topology, then this might be a really good choice. So the great thing about small multiple is that by just using only one color here, you can draw the graph as you like it. So you can judge all the connections and so on in all of the little views. So you don't lose anything in terms of topology-based tasks. The different approach would be data-driven node positioning. So here you don't position the nodes based on some force-directed algorithm, but you position the nodes based on some value. So let's say, for example, I have 2 dimensions associated with my nodes, they're both numerical. Then I could simply say, okay, node A, the number of whatever, or my average grade versus my age, something like that for various people. And then you could simply position each node as in a scatter plot and then plot the edges on top of it. And so here is an interesting video about that.
In this video, we present GraphDice, a system to visualize multivariate social network that supports easy and flexible navigation in network attribute space. In the main visualization window, an overview matrix presents all possible attribute combination plots as graphs. The user can focus on a subset of nodes by creating graphic queries of different colors. She makes a lasso selection to create and refine selections through usual Boolean operations, as in Photoshop. Multiple queries can be activated at a given time to mark different groups of interest, like the strong connected communities the user has highlighted in this co-authorship network. The user can then explore how the community actors are spread from the point of view of other attributes by selecting a new plot in the navigation matrix. There is a 3D animated transition between the nodes and the lengths of the current plot to the new plot, as well as for the convex hulls that correspond to the queries, keeping one attribute dimension consistent during the animation. The user also has the option to control the speed of the 3D animation by invoking a menu with the left mouse button. While dragging, she can observe in detail the actor's motion during the animation and see the correlations between the 2 attributes she is animating back and forth. The 3 state buttons on the right side also allow for exploration, for example by zooming into the selection. The zoom level gets adjusted based on the query selection. At any moment, she can go back to a previous selection state, as every new query is stored in the query history. She can hover over one of the thumbnails for a quick preview of the stored query, and click to retrieve it. Clicking twice restores the plot view to where the stored query was active.
So this probably reminds you of the video that I showed you about scatter block matrices. The scatter dice video, and it's actually the same dice. And probably use the same software framework, and they just thought, okay, how can we use the similar things that we did for scatter plots now for graphs? But I think it's a very smart idea. Like if you really have this kind of data that is suitable to plot that, I think this is a good approach to do this. Of course, this is limited in terms of scalability, and for some, like, and of course the topology suffers a bit. So here, in this case, it works really well. That's probably why they showed us here. But it could be that your values are, for many nodes, are very similar, and then suddenly you don't see the edges anymore. Yeah, so then I wanted to talk to you a little bit about a technique that collaborators of mine and I developed together. And here the idea is that we take a graph, that we give you some kind of like idea of what the underlying values are, but then we use interaction and to essentially extract a path, and for this path we would show you detailed data. So here on the left you see a biological network, a pathway, and each of these nodes is color-coded. So it's pretty faint because the values are very homogeneous, but like blue values mean it has a low value, red values mean it's like on average a high value, and here like many different nodes are averaged together. So I'll walk you through how that essentially works. So fundamentally, if you think about this, if you have experimental data and pathways, or if you have attributes and networks more generally, you have a problem that you cannot, like for biology networks, you cannot account like these graphs. They give you like a general summary of how something happens in a cell, but you typically cannot account for variation that you find in real life data. So branches in these biological graphs can become inactivated. So let's assume, for example, something bad is going on, like somebody gets cancer. So for example, one gene that regulates the cell death is turned off, and therefore cancer proliferates. So that could be because one of the branches in one of those networks is inactivated. For example, because a gene is mutated, or gene expression is changed, or even a branch could also be activated because I'm targeting it with a drug. So like, what the problem here essentially is that you have these networks, and then you have many node attributes. So here you would have like numerical data, and here you have categorical data. For each node you would have like a large vector of those, and you try to map all of this onto a single node. And of course this is really a tough question. So what people typically do is what I like to call good old color coding. And good old color coding works well if you have like only a single vector, then you can clearly map that. But if you have multiple vectors, then of course it doesn't really work that well. And like as I showed you before, people have tried to do this with many different approaches. So here's an approach where little rectangles essentially cover 5 or 6 different conditions. But as you can see, scalability is limited here. So what we need to do is we need to be able to really deal with large numbers of experiments, large numbers of attributes. So for example, in biology, large data sets nowadays have typically about 500 experiments. And then you have multiple groups and conditions. So for example, you could have, let's say, you could divide people based on their gender, you could divide people based on the subtype of their disease, or you could divide them based on did get treatment, did not get treatment, which type of treatment did they get, what time, and so on. So always these groupings and conditions are important. And then you have different types of data. So you have numerical data, you have numerical data of different scales, you have categorical data, normal data, and so on. So everything can be mapped to a node. And then this is the fundamental challenge. We need to support multiple tasks. So we need to be able to explore the topology of the pathway and also to explore the attributes of the nodes, the experimental data. So what we try to do here is that we try to support both of them. So what we do is we take this network, and then we let a user define a path that he or she is currently interested in. And this is actually how people like explore these networks in detail. They don't need to see everything at once, but they kind of like want to see, okay, what is going on in this particular cascade here? So somebody can select this path, and then we can extract it. And so you can see the path here, like as it's shown here, is now like from A to this compound to D to E. So here we have like a linear representation. No matter how these nodes are laid out, here we have a linear representation of that. And to the left of it, we preserve as much of the topology as possible. So we tell people there is another, like there's an incoming edge from B, there is an outgoing edge to C, and here is an outgoing edge to F, and so on. And the great thing about this is that we have space on the side to actually plot the attributes. So here we could say group 1 of dataset 1, group 2 of dataset 2, and group 1 of dataset 2 could be here. And then on top of that, you can plot additional attributes about these individual elements, for example, gender or age or whatever. So this is what it looks like. A user would select a path in here, and the system would dynamically extract this path and like try to preserve as much of the topology, and then show you the attributes here in little bar charts. And then you could extend that path, and the system would continue to extract that. And then you can essentially judge how does that network, how does that path really behave under these various experimental conditions. So here's a live demo of that system. So here you can see on the right, the path that is brushed is dynamically extracted. And then we can extend that to really show the detail about the experiments. And so here you can see that in this case we're showing about 50 values for each single node, and of course like showing 50 values on top of any of those nodes is not very feasible. So this is essentially now like mainly a tabular representation. So here we have the topology information, and then we have this tabular representation, and there's many things that we can do to that. So we can show it to you as individual bar charts, but we can also aggregate it. So here we use box plot instead of individual bar charts for like to aggregate multiple experiments. Here we use histograms and so on. So like this is just what you can do. Like here you can essentially apply everything you know about tabular data visualization now to graph visualization. And so this is one example of why this is important. This is actually a real finding that one of my collaborators at Novartis found. So they were looking at, specifically, this is a cancer-related pathway, and they were looking at the response of these cancer cell lines to two cancer drugs, erlotinib and lapatinib. Those are two popular cancer drugs. And so these values here, in these bar charts, they plot what is called IC50 values. So these values show you how strongly a cell responds to these drugs. And so the lower the better, essentially. Like if the bars here are low, it means the drug works against this cancer for this cell. And so here every single column corresponds to one cell line. So and here we can see that for this drug, there's quite a bit of cell lines that actually for this, where this drug works really well. And it looks like there's a strong correlation between the low values here and the high values here. So that's kind of probably the reason. Like you can say the people that have a high value in RPV2 respond well to lapatinib. So that's like an interesting piece of information. But then they were like trying to look at, oh, there's actually two cases that don't really fit into this picture. So what about those two, the golden one and the orange one here? And so that's where the topology comes in. So they were looking at this, and then they looked down the path, and then they found, oh wow, this gene here down the path is actually completely shut off. And so this is in this case the reason why this drug doesn't work for those patients. So you have to like have a high expression of this gene here for this drug to work, but you have to have like a decent expression along the path as well. So these kind of like combined judgments of topology and experimental data are really important in many cases. Okay, so now I have a design critique for you, and it's about Connected China, which is a project by Ben Fry. We've seen a couple of his visualization techniques. This is let's say a big project that is really like was sponsored by Reuters, and they put it on the website, and it's really like the idea is to let people explore the power networks in China. So take out your computer. I have spreadsheets here. We'll take 10 minutes this time because this is like a very complex visualization, and take your time to play with it and explore what is there. Okay, so let's talk a bit about this. What are the data types that we see here? Yeah, let's start somewhere.
Everything.
People, correct.
People and their connections.
Exactly. And their connections and like, is there more about the connections? Like, is there, what kind of connections are there?
Also
Well-
connections. They have it family
Sorry?
so they have it as like a family connection and
Family connections, but it's only one of them. There's
then there's coalitions and leaders and sort of how they're divided up.
exactly. So if we think of this from a data structure perspective, like we have the people would be the nodes, and then the edges would be these relationships, and there we have different edge types, like family relationships, social relationships, coalitions, and so on. Okay, what are other data is there?
Career trajectory.
Yes, career trajectory. So like there's a different plot where we have this temporal aspect of it. And then something else.
Economic data is contained in the map as well. Economic and economic and population data is included.
Oh really?
Right there.
In this one?
Yeah, if you go to interactive map.
Okay, I didn't look at this closely, but yeah. I was mainly shooting for the network aspect here. Yes. So like for nodes, what do we know about the nodes? It's people, correct?
You see hierarchy, who's the mentor of who and who promoted who and who's promoted by who.
Yes, these are essentially like edges and edge attributes. But we also have like different types of nodes, right? So like we have different types of nodes and we have different categories. Like you can see what they show, these categories here, like the golden sons-in-law, past and current leaders and princelings and so on. So like every node is essentially assigned to a category here. Okay, so how is this represented? Like what would be, like, let's say you get this network and you're, like, if you throw this into a force directed layout, what would happen probably?
It'd be a big mess.
Giant hairball.
Yes, it's going to be a hairball. So what is the strategy here to kind of deal with this problem?
Filters and queries.
Exactly. So we don't see the complete graph ever. We always see the graph from an egocentric perspective, always from the perspective of a single person. So in this case, I've selected the current president of China. And so we see like his relationships. And what do these two layouts here mean? Like these two circles? Yes, correct. So this is really about, like here, these guys have thought about what matters in social networks, right? Is it the 5-hop relationship? Like if I know a friend, like if I have a friend of a friend of a friend of my cousin's aunt, that doesn't really matter much to me.
You just said something. I didn't hear what it was.
Okay, so they really thought about what is meaningful in terms of a social network, what is meaningful in terms of relationships for power. So, and here the reasoning, I assume, is like the primary like direct connections and maybe like a second level of connections. And I assume that all these people like know each other, but they might not know each other like not like this guy might not know every single person down here. He probably does, but he doesn't have like a strong phone connection. Okay, so so this is really also the role of interactivity. And then the other interesting thing is, of course, what are other aspects that are interactive here? So the links are actually not shown. The links in this case are implicit. So we have the center of the focus essentially, and we know that he's linked to every single node in this along this circle. So by using this layout, they actually don't have to draw any links for that. And they know that we know that there's like a second hop relationship to any of those guys back here. But this is of course not obvious how that works, but so here you would have to use interaction to see this. So like the president is connected to Yang Zemin, and Yang Zemin is in turn connected to all of those people here. And then if we like change the focus, this updates. Like what is the role of the nodes here on the left? Did anybody notice that?
Family members.
Yes. And so here, what is the layout?
Generations.
Exactly. And how are they encoded?
Size.
ISO values,
ISO values?
same value, same
Ah.
generation.
Yes. So and actually they're redundantly encoded. So you have the 3 lines here, like, and the left line here is the parental generation of the currently selected node. Then this is the same generation, so all the siblings and cousins and so on. And this is the children generation. So like you see these family relationships down here, and which is kind of interesting to that. Oh, like if you think of this is about political power, and in theory, of course, family is and shouldn't play a role in political power. But it's obviously not the case in the United States, so why should it be the case in China? Yeah, okay, so, and then we can switch to different types of attributes. So we can switch between families and coalitions and leaders and connections and so on. So, what is this one here? Yes, so this is kind of, what are the nodes here?
Different political positions.
Exactly, so we're switched here from people to positions. Like these are abstract concepts. This is what the structure of the government is, and not what the individual people are. So you can like hover over and see what the various things mean here. Again, once you click a node, you get like details on demand. So this would be, you can look at the government, you can look at the party, and you can look at the military. And then here we briefly talked about this. So what do we see here?
Their advancement through their age, isn't it? Like they're where I started and I was there for this long and then I rose to this type of position after this long type.
Exactly. So it's a combination of time and rank, and the person is shown as like having a specific position for a while and then he's promoted to another position or he retires eventually. So and this is like, what is the time scale here? Yeah, it's age. It's not real years, like in terms of like as they pass, but it's age. So it tells you like who made like a stellar career very quickly. So this is another kind of attribute, of course, like what is the history and how did the network change and so on. And here in this case, the layout is like, this is still, well, it's not strictly a network anymore, but it's more of a temporal sequence of like, let's say, categories. So here the layout very much drives, like is driven by the positions, and you can see where the individual people end up. And so we can see, not surprisingly, that the people that are very powerful have made a very quick career. So, what do you think about this visualization?
They know a lot about China.
It's a little bit overwhelming at first, but I think you could spend a ton of time and still be interested in it because there's a lot of information.
Yeah. So who do you think would be like a good audience for that?
Poli-sci people.
Yeah, so do you think that like people who read Salt Lake Tribune would be super interested in this?
No.
No, so this is really like, maybe this is a little bit much for like a general audience. It's really going deep, and it's a little tough, at least for me, since I don't know many of the actors here. It's a little tough to get a feeling for the data. It would probably work better if it were, for us here, it would probably work better if it were European or American leaders. We could probably explore it more because we're more familiar with the terms. But what do you think about the visualization approaches?
I think the shifts from leadership to family are kind of jarring. When you try and relate them, you know, you see like a million stars and they all move somewhere else, and so it's hard to follow that.
Exactly. So the animation is tough. Like if we switch here.
Yeah, if you go to coalition, then
Yeah, so it doesn't really help too much. You can only see the labeled ones. That you can kind of like trace the labeled ones. So if you look at these three guys here. So another observation here is that this seems very, very like. Do you think this? There's a lot of annotations. Do you think this is like? Or at least in my opinion, this lives also from like a very, very tailored representation to this specific data set. So there's lots of details about the various people. There's like annotations on every level and so on. So this might be tough to do for a general graph problem. Maybe it would work for social networks. Maybe one could try to actually create this dynamically for any kind of social networks. So, opinions? Do you like this?
I like it. I think it's
It'd be
cool.
fun if it was for the US too. Like if you click on different countries.
Yeah. Yeah, so, any other opinions?
It'd be crazy to update this all the time.
Yeah.
I kind of think this would have worked better in the native language
In the native language, in
for Chinese. I mean, like, I felt like there's a sort of contradiction there, because you have it in English, then the translation, the stuff loses in translation, because I can't match up what they're talking about until I see the Chinese term in there.
Okay.
So, I think Chinese, like, their native people will probably be more interested in knowing this in depth, because they're very sort of involved in this. And people here are probably not going to be as interested to know this so thoroughly, and then it's just...
That's definitely correct. So like the audience question is tough, and of course like the aspect of like losing in translation, but like if, at least for me, it's better that there's some English in there. Otherwise, it would be really lost. But I guess also the idea here is to like for political science people, for analysts to understand what is going on and so on. This kind of information might be valuable. So this was actually like a project. I know a little bit more about this project. It was a project that was sponsored by Reuters. It kept this company, Fathom, like it's a 10, 12 person visualization shop in Boston, and it kept them like say 50% of the company busy for almost a year. So there's like 5 man-years in this one. And it was big. Like it was a big feature on Reuters, but they have since not like they're not hosting it via the Reuters website anymore. I think probably because they didn't update it. So this is updating the data as one of you guys mentioned is tough. The implementation here, guess what?
D3.
It's not D3. It's all handwritten canvas.
Oh, that's miserable.
it's a lot of JavaScript.
Yeah, it's a lot of JavaScript. Well, part of this was, of course, that this is a little bit older, as you can maybe guess from the aspect ratio. It's pretty like 2013. Well, a little bit older. D3 was around then, but it wasn't as widely popular. Yeah, so like my personal opinion is it's very good, but it's also very complicated. It's like an expert system. So it's not really something that you would put on the New York Times website that is really for a general audience. It's really for somebody who has a deeper interest in finding out the relationships. But I really like the essentially the approach to dynamic details and the approach how they lay it out based on like one central position. So it really manages to get like a very big, messy data set into like something that is parsable. I wonder, of course, how like faithful is it? Like if I knew the real data, is it really like a good representation? So is there a lot of people that fall off the edge down here, or yeah, is there like a lot of additional stuff that we want to show here? So yeah, but generally, I think it's very well done. Oh, so here is like this overview representation, and here they only selected a couple of people, and yeah, this is kind of like a pulls in based on the categories. So here, the categories are these fake nodes that pull in the various people. Okay. Any other comments about this before we move on? Great, so let's talk about matrix representations. So we have seen a lot of matrices in this class. We have not talked about them too much in terms of like what do they mean for a graph. And so like this here is on the left the node length graph, and on the right there is the matrix representation. So how the matrix representation works is that I plot in the rows and in the columns, like I plot every node corresponds to a row and a column. And so the cell is filled in when there is an edge from A to B. You can see, okay, here is an edge from A to B, therefore the cell is filled in. There's no edge from A to A, so I could have this loop here, and then this would be filled in. I have an edge from, like, of course this is like a symmetric in this case, like A to B and B to A. I have an edge from A to C, but I don't have an edge from A to D and A to E. So like by essentially like looking at this, we can see like we can reconstruct the topology of the network. So like just looking at this, you can already guess what is good about these kind of representations and what is bad about this representation. So like for example, do you think it's easy to find a path from A to E in this representation? No. But do you think it might be easy to, like say I have edge weights and I want to color code them, that might be a very good task here. So like if I say A to E would be airports, and I want to visualize how many flights there are per day, then I could simply color code this, and then I could get like an overview of the highly connected components very quickly. So here are a couple of other examples, what common motifs look like in a matrix. So like here we have this like one central point connects to every other node here. Here we have this bipartite graph. Then here we have this network here, and here we have this click. And so these in this case are directed. So for an undirected network, these two halves are symmetric. For a directed network, they're not symmetric. So they're like there's an edge from A to B is not the same thing as an edge from B to A. For topology-based tasks, they're well suited for neighborhood-related tasks. So for example, to find out what are the neighbors of B, that's very easy. Like it's A, C, and D. But it's really hard to find the path from A to C. So from A to C, let's try that. Okay. Somehow the layout here is really screwed up. So from A to E would be like we go here, from E. Okay, we go like we have to look at this one here, and here we have the connection from E to C. So this is pretty tough to do, and you have to sit down and think about it. So these kind of like topology-based tasks, they're really not well supported by these matrix representations. Here's another example of various structures. Like you have like this little bit more complex graph, and what the structures correspond to. in this matrix layout here. And as with any matrix, the order here is critical. So this is again the Lewis-Araber network, and if you like just order them alphabetically, you don't really see anything. But if you do some kind of clustering, you see, okay, there's this group of people that all know each other. There's this group of people that all know each other, and then here is the outlier that essentially interacts with a lot of those people. And this is, of course, the main character of the play of Valjean. So he's interacting with many of those people here. So this is like a very common thing. Like to have, like if you look at a network in a matrix, you will often see these connected components, these cliques, with very sparse connections outside of this. So what are the pros and cons of matrix representations? Well, they can of course represent all graph classes except for hypergraphs. So we can't draw hyperedges in them. So if you have hyperedges, it's not a good visualization technique. It's really about focusing on the edge set. So if the types of connections are important, then they're great. It's not so much about the node set. It's very simple to lay out. We have a grid. You don't have to do any complex computation. It's very fast to lay it out. It's very well suited for attribute-based tasks and edges by coloring the matrix cells or by even embedding little glyphs within the matrix cells. And it's also well suited for neighborhood-related topology-based tasks. So like, what are the neighbors of A? That's easy. Of course, the cons is it's not suited for path-related topology-based tasks, and we have this quadratic screen space requirement. So any possible edge takes up space. So kind of like from this follows, this is a very good technique for very, very tightly connected graphs. So essentially, like if you have almost complete connectedness in your graph, this will be a great layout because you have to reserve the space for every single edge anyways. But if you have a very loosely connected layout, it might not be a good layout because then here you can see that essentially like probably 80% of the screen space are wasted, 80% of the cells are empty. Whereas if everybody knew everybody else and we just want to show like some kind of strength of the connection, then this would be a very good representation. Here is a special case of this for genealogy. So there's a video that I wanted to show you.
Creates a novel interactive visualization technique for large genealogy datasets based on a layered matrix representation. This representation has no crossings, which makes it more scalable than the traditional genealogy visualizations. For example, here is a genealogy of 700 individuals presented by genealogists, and the same genealogy represented by a node-link diagram. Let's start with a simple genealogy of the Simpsons TV series. The basic elements of the genealogy visualization are generations, individuals, male and female, families, and relationships within families. By family, we refer to nuclear families consisting of two parents and their children. For example, in this family, the square of the family indicates that Homer is the father, and the circle that Marge is the mother. The circles below show that they have two daughters, Mikey and Lisa, and one son, Bart. Similarly, Marge's parents are Jacqueline and Clancy, and her sisters are Selma and Patty. More generally, cells above the family icon point to the parents of the family, and cells below to the children. Cells on the left of individuals show which family they were born into, and cells to the right showing which families they participate as parents. In the Greek pantheon, for example, Zeus is a father in more than one family. He married Hera, with whom he had 4 children, and coupled with other individuals, including one from a different generation. We implemented the genealogy visualization in an interactive genealogy exploration system. The system consists of a main visualization window, an overview, a query window, and a timeline. For this family of 700 individuals, we can use the overview to quickly pan across the genealogy, while the main window automatically zooms out to fit as much content as possible. At the same time, the timeline shows the time span of the main window. By selecting an individual, we can see all its ancestors and all its descendants. We can toggle the visibility of ancestors and descendants by clicking the selection. By dragging the selection, we can rapidly switch to other individuals. We can also perform multiple selections in different colors. Since Zeus and Poseidon are brothers, their ancestry is displayed in both colors. We can use this color blending feature to find common ancestors. For example, in the Bible genealogy, we might look for the common ancestors of Mary and Joseph. In the overview, we can see where the two colors blend, and find out that the most common recent ancestor is King David. Conversely, we can use the color blending to look for marriages between two bloodlines. Matani and Shalom are the first children from both bloodlines, but the overview also tells us that this mixed bloodline seems to die out after a few generations.
Okay, so this is
We're observing the overview while dragging
a special type of graph. Like it's not a tree, but has like strong tree-like structures. So that's why they can make use of this layout. And I think this is a very good like specific representation for this kind of data. Okay, so we talked that matrices have downsides and node link diagrams have downsides. Why don't we use them both together? And that's of course what people have thought about before. And this is what this technique node tricks. So the idea of node tricks is really to use matrices for tightly connected components and to use links to connect other tightly connected components. So here you can see this is like the research collaboration within Xerox PARC, and this is on the University of Maryland group from one specific, focusing mainly on mentioned Ironman. And then you can see the relationships here. Like you can see this, there's only two relationships in here. Like showing all of this in a matrix would be much more like wasteful. And there's another video for that. So they start up with a node link layout, and then they dynamically transform it into a matrix. Like this here is a click, so every node is connected to each other. And again another click, and notice that they show the labels here in this case, but you can't really see any of the labels in the other case, in the node link diagram. Yeah, so I guess you get the fundamental idea. Let's just see what on the tabletop. But the fundamental idea is really to try to use the node link layout for the loose connections and use the matrices for the tight connections. Okay, so this kind of completes what the things that we can do with general graphs. Of course, there's more that you could do, like aggregation and so on. But I'll leave this up if you want to read about it yourself. I can give you a couple of pointers, like how can you deal with larger graphs, how can you deal with queries and so on. So there's a lot of work in that space, but it would go a little bit too far. Now let's talk a little bit about implicit layouts, and implicit layouts are really specific to trees. So here is an example of 3 different implicit layouts compared to 1 explicit layout. So here we have this tree from A to B, C, D, and E. And we can have this implicit layout by inclusion. So B, C, D, and E are included, are children of A because they're included in the area of A. Then we could have them by overlap. So an element is a child of an element, or a node is a child of another node if it is overlapping with that node, or it is also possible by adjacency. So here we have B is a child of A because it's adjacent to A, so there's no gap between them. And so here you can clearly see why this doesn't work for graphs, because if I had an edge from C to D, I would be in trouble because I would have to try to find, like I could do it for having an edge from C to D, but if I have the general cases of multiple things connecting to each other, the layout would simply be too restrictive. So that wouldn't be possible to do. And the most common implicit layout are, of course, tree maps. So here, like this is a figure from the original tree map paper from '91. So you have like this hierarchy here, and this is the representation. But it's maybe a little bit easier to read here. So you have, in this case, a parent node. The white one, like this essentially like defines the whole space. And then you have 4 children. The green and the yellow one, they're leaves, so they're like directly shown here, and they're of equal size to all of the others. And the blue one has, again, 4 children, so these 4 segments. And one of the children of the blue one has another 4 children, so these segments. So this is this essentially like subdivision, and the hierarchy, like we know that this here is part of this larger rectangle, is part of this larger rectangle, and therefore we can explicitly reconstruct the hierarchy. So this is great, like if you want to really focus on attributes of the nodes. For example, in this case here, this is a zoomable tree map, a New York Times visualization, and this is an how is the budget, like the 2012 budget, composed. So you can see, and here it makes a lot of sense. There's a hierarchical component to it, so like the various departments and the various sub-areas. So for example, we have defense, you have procurement, operation, maintenance, military personnel, and so on. These are all parts of defense. And then here, like, you would have agriculture and so on. So in this case, you have like not a very deep hierarchy. You have like a top level, like the root, and then you have the departments, and the departments have the various positions. But what this really is about is telling you how big the various parts of the budget are. So it's about the size of the node attributes. So you can see like health and human services, there is, well, Medicaid. Yeah, this is Medicare and Medicaid. So you can see that health and human services have like a large proportion of Medicaid, and you can like look at these various things here, and if you click one of those, you would zoom in. Then you see, okay, food and nutrition services, forest services, farm service agency, and so on. And the color here again encodes the change with respect to 2010. So you can zoom out again. You can see that there was like an increase in Medicare, there was an increase in food and nutrition service, but there was a decrease in employment and training administration. Okay, so that's the fundamental idea of the tree map. Tree maps are really good in terms of scalability. So here is a tree map of 1 million items. And this still is helpful. So like I personally use this to clean up my hard drive. But this is like an interactive visualization of the files on my hard drive, and I typically run out of disk space eventually. So when I try to find what is actually causing this, I like open up this tool. This is called Graphical Perspective. There's Sequoia View for Windows, and there is others for Linux. But what I really am interested here is like the big blocks here, and then I would essentially like I know, okay, this region here, these are my pictures and my like the personal videos that I've made. So I'm probably not interested in deleting any of those. But here are kind of like the movies. So maybe something is outdated in this sector here, and of course like these big blocks tell me, okay, this one, if I actually delete this one, it will save me quite a bit of space, whereas it's maybe not worth my time to drill down into what are these little things here if I just want to free up this space. So you can see like the hierarchy is pretty deep here, and it's highlighted by these rectangles. So like this is like the first level of the hierarchy, second level of the hierarchy, third level of the hierarchy. And of course this here starts at my home folder, not at the root. If it were starting at the root, this would be like even more cluttered, but these are already, I think, are 400,000 files or something like this. So it's quite scalable. And you can see that I have a mess on my hard drive.
I like how it shows which file you're moused over at the very bottom. You can see.
Yeah, exactly. But that's important because you kind of need to know, is this actually like worth deleting? Like these would be my wedding pictures.
Definitely worth delete.
Yeah, okay, this big block here is all your homeworks, homework 6. A zip file of all your homeworks, a zip file of all your homework 5. And you can see that homework 4 is much smaller. So that's the data sets essentially that drives it. And I will delete those once we're done with this class. Okay. So we talked about this like sunburst briefly until here. The encoding is, instead of like having containment, it's about adjacency and in the radial layout. So this would be the root, and all the elements that are adjacent to it, like this segment here, is a child of it. This segment here is not a child of it, and the angular, the angle actually tells you the size of the sum of all its leaves. So the difference between this radial layout and the tree map is that I can like get a better idea of how big the segments are. Like I know immediately this one here is my biggest folder. I don't have to look at the individual files. So I personally like this one a lot. Here is this zoomable sunburst that I showed you a while ago, so I can click on any of those nodes and then I would drill into that part of the tree, and I can go back out by clicking on the root. Clicking here would zoom in here, and here like there's two different switches here. I could either like do this by the count. So here every single segment, every leaf has exactly the same size. So I can, if I go out here, I can judge how many items are in this subtree, or I could do like some like other attributes like mapping here. So like you can see that these leaves have a different like size or a different angle. So that would be, for example, file size. And there's actually tools, I know for Linux, there's FileLight, which does this for your hard drive. And I actually prefer the sunburst to the tree map for storing my personal hard drive, yeah.
So, and like we've talked about, pie charts are awful. And
yeah.
This looks like it's a very elaborate pie chart.
It is. But you, like a pie chart only shows you proportion. This also shows you hierarchy. So there is more data in here. And so there's like, of course, what you could do is if you want to like get rid of the angle, you could actually like flatten this out and make it an icicle plot. But somehow like it's less intuitive. Like it's less. I don't know exactly. I don't have a super strict answer why, but I think like here it's less about judging the specific quantities, but really getting a sense of the hierarchy, and therefore I think that the angles work okay. Whereas in a pie chart, yeah, typically like that wouldn't be such a good idea. And like of course here zooming makes sense, right? In the pie chart, one of the problems of a pie chart is that you get these tiny little segments that you can't read anymore. But there's not really much point in zooming into a pie chart. But in this case, actually, there is like a natural way of zooming by navigating down the hierarchy. So it has some of the same problems, but it's like, I think it's a way better technique. It makes better use of the angular. Like, and there's not as like good of there's not as many good alternatives as there are for pie charts, in my opinion. But that's a very good comment. So here is like another implementation for like how we could do these details on demand. Like here, like we have a focus and context technique. So this segment that is clicked here, this little segment here, kind of like is popped out and makes up the outer ring, and you can still see the whole hierarchy in the middle. So this was part of the original technique. So here would be the corresponding technique if you kind of unwrap this into a linear representation. This would be what's called an icicle plot. So here's a comparison of the same hierarchy with 4 different implicit techniques. So the icicle plot, then here we have the tree map, and here we have the sunburst, and then here we have circle packing. So you can see clearly that there is like difference is that this is really like focuses very much on the leaves. You can see the individual attributes of the leaves very clearly, whereas those two here, they focus more on the hierarchy. So it's, for example, it's harder to see that that these files here are 4 levels deep. So this like would probably be this one here, and you can kind of judge that, but it's harder to judge. Yeah, and the circle packing is kind of popular with people using D3, but I haven't really seen many serious applications of it. But of course, like here we have the root, and then within it is the, like this would be the second level, and this would also be on the second level, and so on. And the leaves are color-coded. So depending on your task, I say like each of those 3 here can make a lot of sense. This one here can make a lot of sense if you, for example, want to connect it to something else. If you like, want to show the evolution of a hierarchy, you could easily like imagine that you have 2 or 3 different icicle plots above each other and then connect them with your ribbons. This really makes sense if you want to focus on the size of the individual elements, and this is kind of like a compromise between hierarchical structure and the size of the leaves. So here is the like pros and cons of implicit representation. They're very space efficient, so you've seen that we can do like 1 million leaves. We can lay out 1 million leaves. They scale very, well up to very large trees. They're well suited for attribute-based tasks, at least for the sunburst and the icicle plots, but it depends, of course, on which encoding you use. They're very suitable for topology-based tasks depending on the actual encoding, but typically they're very well suited for attribute-based tasks on the node set, so node attributes. The cons, the biggest problem, of course, this only works for trees, but of course trees are important. The node positions are used to represent the edges. They can no longer be freely arranged, so we can't really, like, say, do a tree map on top of a map. There is some, like, we've seen this work by the people from UCL, from London, that did this mapping to London districts, but there they only had, like, approximate locations. So, like, if you really want to, like, have strict locations, it doesn't really work. It's useless for anything that is related to edges, because the edges are not shown, not even like, they're implicit, that's why they're called implicit representations. So if you have edge attributes, you can't use it. And then spatial relationships, such as overlap or occlusion, can lead to occlusions, so especially like in the tree map case. So if you want to visualize a tree, there is a nice website. It's called treeviz.net, and it is a collection of every single tree visualization that was ever published. It takes a while to load all of the pictures.
Downloaded it and
And so there's a couple of crazy ones. The strata tree map, for example, uses like a 3-dimensional version of a tree map. So you can actually, like, say dimensionality, only show me the hybrid, or only show me the 3-dimensional representations. And so, like, here we would have this 3D sunburst in terms of a sphere, or this is actually a 3D beam tree, which is like uses 3D structures by alignment. So, like, things that touch each other have like a parent-child relationships in this 3D space, and so, like, you can see that this is from 2002. I would say these were the wild days of InfoVis, where you could still publish things like
get away with anything.
Exactly. And it was still very cool to be able to render this on computers interactively. So you have these like botanical representations and so on. So there's like a lot. But the point of this one here is that it's not curated. It doesn't recommend do this or do that. It's really like a what is possible. Like, what can we actually do? So they have this, you can do by dimensionality, you can divide by dimensionality. Here you have explicit layout, implicit layout, or hybrid layout. So here we would see node tricks pretty quickly. There's node tricks. Oh well, node tricks works for general graphs, so that's why they probably didn't include it. Implicit is of course the tree maps and so on. Explicit are any kind of networks. And then you could have like alignment based on radial alignment, based on free layout or axis parallel alignment. And you can search and you can click on any of those and you can actually like go to the paper, download the BibTeX file and so on. So this is like a tool by a researcher. So in summary, like there's 3 different types of graph visualization techniques: node link diagrams, the adjacency matrices, and enclosure or implicit. Like in the book by Tara Manson, she calls it enclosure. I like to call it implicit, or because of the edges that are implicit. And the big difference is, of course, they don't work for general networks; they only work for trees. I just before finishing this up, I actually spent the whole lecture on graphs. I wanted to show you like a couple of tools that you can use. So of course you can do your own layouts, but typically in D3 now, but you can also just load a network into a tool. Gephi is one of those tools. It supports things like clustering or calculating page ranks and so on. So if you just want to explore a network that you have, Gephi is a good choice, and it's a general purpose graph visualization tool. Cytoscape is more targeted towards biology people, but it's very big within the biology space. So there's lots of plugins, like hundreds of plugins for Cytoscape, that allow you to do things like mapping experimental data and so on. Cytoscape has a web component, so you can export your Cytoscape graph into like a website. And then there's also Network X, which is more or less like a library for Python to do path networks. And of course there's graph databases and so on, but if you're interested in digging deeper into this, I encourage you to explore it. So then next time I will be talking about maps. Sorry that we didn't get to that today, but I do like graphs and I think they're important. So see you on Thursday.